So delta G determines the spontaneity of reactions. The equilibrium constant determines how far the reaction goes. So if we have a larger K, then we have a more negative delta G. The products are going to be favored. If we have a smaller K, we have a more positive delta G. And just for the sake of time, I'm not going to derive this. So delta G is equal to negative RT natural log of K. The bigger this is, the more negative delta G is. I'm going to skip that one. Calculate the standard free energy change at 298 for this reaction, and they're giving us the equilibrium constant. So we're going to use that equation I just wrote down. Negative RT natural log of K. The value, the number that you use is going to be dependent on which units are going to work out in the equation that you're using it. Here we're calculating things with energy, and so we're going to use the one with joules. There's a relationship between liter atmospheres and joules, but we don't have to do that calculation if we just use the other value of R. Temperature, natural log of 81.9. Wait a minute. It's 10.9. Any questions? If we put Q in here, well, we're just not going to go there. Just not going to do that. So we see that free energy change depends on the equilibrium constant, and free energy change also depends on the temperature. So that gives us another crazy equation. This is the straight line form of it. I guess I should do this. Whoops, not that. Oh, I don't know what I'm doing. This equals this. This also equals that. So this equals this. And then you can rearrange that equation. So that's what they did here. They took that equation and rearranged it to the form of a line. So the natural log of k is equal to negative delta h over r times 1 over t plus delta s over r. This is the slope. This is the intercept. Natural log of k is the x, is the y, and 1 over t is the x. So we can get a pretty good estimate of delta H and delta S by measuring the equilibrium constant at different temperatures. And that's something that you can actually measure. We did that. There's also a 2-point form of that. And this is a lot like a previous equation that we used, the Arrhenius equation. So we can find delta H if we have K at 2 different temperatures. And so that's not too hard to measure either. If you want to know what the equilibrium constant is at a different temperature without doing an experiment, if you know what delta H is, you can calculate the equilibrium constant at a different temperature.